Hello and welcome to Duke Williams online tuition for financial management. My name is William Amma, and thank you for joining me for this second part of our unit number 16, DCF specific applications. Please ensure you have downloaded the corresponding slides for this video so you can follow me with the discussions. Looking at part 2 of our unit number 16, specific applications. In the first part, we looked at the decision to lease or to buy an asset. In this second part, we will be looking at asset replacement decisions. Now, the DCF technique can be used in asset replacement. Now, when you are making asset replacement decision, you use the DCF technique to assess when to replace the asset and how frequently an asset should be replaced. When should you replace the asset and how frequently an asset should be replaced. The analysis will calculate how long to keep each individual asset before trading it in and replacing it with a new one. The analysis will calculate how long to keep each individual asset before you trade the asset in and replace it with a new one. The somewhat unrealistic assumption in the analysis is that an asset will be replaced by an identical asset, but it is not often the case. It could be replaced by a more superior asset as a result of technological advancements and even completely different assets. Now, asset replacement decisions. There are typically several effects on the replacement period. As the replacement period gets longer, there are typically several effects as the asset replacement period gets longer. So maybe the asset could be replaced in 2 years, but you are deciding that we should replace it in 3 years or even to 5 years time before we replace. Then you should know that there are several implications as the replacement period gets longer as you hold the asset for a long period. Now, if that is the case, what are some of the effects? The annual running cost rises as the asset gets older. So maybe the cost of running the assets will change from 5,000, where it's getting older, it needs more power and so on, to 6,000, and even as it get older, it needs, let's say, 8,000, and so on. So the running cost will rise as the asset gets older. But then the trade-in value falls because the asset is older when sold. So even though the running cost is getting higher, let's say here the trade-in or the resale value, if you are to sell the asset, maybe the asset was bought for 50,000 and it is costing 2,000 to run it, to maintain it, but now we need more to maintain it. For in year 3 we need 6,000, and even if we keep it for 5 years we need 8,000. Now if we wanted to sell the asset after maybe 2 years, we could have sold it for 28,000. But if we keep it for additional year, we could only sell it for 21,000. And maybe if we keep it for 5 years, we can only sell it for 14,000. So guess what? Whereas the running cost is increasing or rising, the resale value is rather starting, we could have sold it more, and now it's going down and down and down and so on. So these are some of the things that we look out for. The effects as the replacement period gets longer. Obviously, holding the asset for longer means that the replacements happen less frequently, so the purchase costs are encountered less often. So let's look at this question, and the question is that an asset which costs 20,000 has the following properties. The asset, it costs 20,000, but the cost of running the asset in the first year is 2,000, in the second year is 5,000, third year 6,000, and the cost of running the asset is 7,000. So you see that the cost of running the asset over the period of time keeps increasing. It costs us more to run the asset, as we have ascertained earlier. But if we use the asset for 1 year and we wanted to sell it, we could have sold it for 14,000. And if we used it for 2 years before selling it, we could have sold it for 10,000. So the trading value decreases over the period of time. I hope that makes sense now. Now, if the discount rate is 15%, what is the most economical replacement cycle for the asset? After how many years should we replace the asset? That is what it's asked. After how many years? Should the asset be replaced? Now, before we go further, in looking at asset replacement, one outstanding formula that you must always commit to memory is equivalent annual cost, or even equivalent annual benefit. EAC, equivalent annual cost, means that you find the net present value and then you divide it by the annuity factor. So having this understanding that you need the net present value divided by the annuity factor, I'll do the NPV as though I'm going to replace it 4 years. NPV as though asset will be replaced after 1 year. What will be the NPV? Or after 2 years, what will be the NPV? What if the asset is going to be replaced after 3 years? What is the NPV? And what if it is going to be replaced after 4 years? What is the NPV? And when I know the NPV, I'll divide it by annuity factor 1 year, annuity factor 2 years, annuity factor 3 years, annuity factor 4 years. And once I have the equivalent annual cost, the decision is always to go with the choose lower equivalent annual cost. We always choose lower cost. When it comes to benefit, we choose the higher benefit. So let's begin by looking at assuming the asset, calculate the present value of 1 cycle of each length. So I'm going to assume that the asset will be replaced after 4 years. Asset to be replaced after 4 years. To be replaced. So look at the question. I hope you have your PowerPoint slides. If you look at the question page, asset to be replaced after 4 years. So in the initial cost is 20,000. And then in the first year, because remember we are not replacing it after 1 year, so the first year the running cost is 2,000. The second year the running cost is 5,000. Third year the running cost is 6,000. Fourth year, because we are replacing it after 4 years, so we incur all this running cost. But when we add all the costs in the fourth year as well, when the fourth year comes to an end, we'll replace it. And how much do we get for replacing it? Is 5,000. So just make a list. The initial investment plus all the running costs, and then the residual value. We discount it at 15% using the present value table, and we multiply the running cost and then let's say the initial investment by the discount factor, and we get the net present value of the cost. So it will cost us 30,612 if we are to replace the asset after 4 years. But remember, we are using equivalent annual cost, which is the NPV divided by the annuity factor. So we have found the NPV after 4 years. Let's go and find the NPV if we are to replace it after 3 years. So here is 3-year cycle. The asset will be replaced after 3 years. So we buy the asset for 20,000 and we maintain it for year 1, year 2, year 3, and year 4. And at the end of 3 years we sell it. We discount it at 15% and we get our present value costs. That's when we will replace it after 3 years. That is the net present value. Then what about if we replace it after 2 years? Asset to be replaced. To be replaced after 2 years. So we buy the asset, we incur the first year running cost, the second year running cost, and after 2 years we replace it by selling the asset for 10,000. We discount it at 15% and we get the NPV costs. And finally, what if the asset will be replaced after 1 year? Asset to be replaced after 1 year. To be replaced after 1 year. Now, if the asset will be replaced after 1 year, it means when we buy it for 20,000, we only need to run it, the running cost for the first year, after which we will sell it. So after 1 year, we sell it also for 14,000, and then we get the net present value cost. So we have 4 different net present value in terms of how much it will cost us if we replace it after 1 year or 2 years, or even 3 years or 4 years. So once we have the NPV cost, we have barely done one aspect of finding how long it should take to replace it. We have barely done the NPV cost. We have barely done the NPV cost. So at 15%, we need the annuity at 15%, so that when we take the NPV cost divided by the annuity factor, we can get the equivalent annual cost. Because we cannot compare year 1, how long it takes to replace it in a year, with that of how long it will take to replace it in 4 years. So we need to standardize this one. so that we can compare. We can standardize the period into a common denominator, and then we can compare. Now, if that is the case, I mentioned earlier that to do this, you use equivalent annual cost, and it's the net present value cost divided by annuity factor. So let's do it for each of the years. Look at the annuity factor for 4 years. And then you see that the equivalent annual cost for year 4 is going to be the net present value that we did, divided by the annuity factor at 15% for year 1 to year 4. When you read from the table, it is 2.855. So this gives us an equivalent annual cost of 10,722. It is equivalent to the cost of 10,722 each year. So read the annuity table and see if you divide this one by the annuity factor 15% 1 year, or you divide it annuity factor 15% 2 years. See what equivalent annual cost you will be getting, divided by annuity factor 15% by 3 years. And then we can compare from our answer which one costs less. So when you read from the annuity table or cumulative present value table, you see that year 1 is 0.870, but for year 2 is 1.626, and so on. So the present value divided by the annuity factor is giving us 10,989 and 11,046, 10,602 and 10,722. So based on the equivalent annual cost, I will choose the one which give me the lower or the lowest, because we want the length or how long it will take to replace it by considering the one which costs us the least. So we choose that will replace it after 3 years. The 3-year cycle is therefore the cheapest replacement cycle at an equivalent cost of 10,602. We can use the same principle when we are finding the benefit to be derived from an investment or a particular activity. The same formula, the same principle. Now, because it is benefit, we will be guided by choosing the higher or the highest equivalent annual benefit. So equivalent annual benefit is the annuity with the same value as the net present value of an investment project. This can be used to compare projects of different lengths. And assuming we have project A and B, and they have different NPV and different duration, to see which one to choose. They have different NPV, they have different durations. So when you take 50,000 divided by the annuity factor 6 years, 40,000 divided by annuity factor 4 years, we find that project A gives us benefit of 11,481. Project B gives us benefit of 12,618. Remember, it's benefit, so we choose the one with the highest benefit. We choose the one which gives us the highest benefit. And in ranking, we'll say choose project B first, then A second. So I hope that makes sense. You now know that if ever you have to do equivalent annual cost or equivalent annual benefit, you need to first of all find what your net present values are and divide it by annuity factor at a particular discount rate. And if it is cost, you go with the lowest equivalent annual cost. If it is benefit, you choose the one with the highest equivalent annual benefit. And that is what we would normally do with asset replacement. Thank you very much. This brings me to the end of the second part of Unit 16 DCF specific applications. I hope you can get to review it over and over and you master the techniques. My name is William Amma. Thank you so much.